Today we are going to be solving problem 4. 4a wants us to draw the HOMO of the allele anion. So one thing to note about the allele anion is that it has 3 pi orbitals. Since the number of atomic orbitals must equal the number of molecular orbitals, there are also 3 molecular orbitals. So let's draw those out. So we have pi 1. In addition, the allele anion has 4 electrons within it. So let's fill in these shells. By definition, HOMO means the highest occupied molecular orbital. This orbital is the highest orbital with electrons. So if we identify that, that's clearly going to be the second one. So the second one is our HOMO. However, we also need a visual representation of these pi orbitals. So let's draw them out. With the first orbital, there's going to be 0 nodes. And as you go up the molecular orbitals, there is an addition of 1 node. So the HOMO layer will have 1 node, and the third one will have 2 nodes. Nodes are regions in which you will not find a density of electron clouds. So just to illustrate the first one, it has 0 nodes, meaning there is constructive interference and all the pi orbitals are in phase, meaning they interact with each other since they're facing the same direction. Now let's draw the visual representation for the HOMO MO. So the HOMO MO has carbon 1, however, carbon 2 is not present, and carbon 3. So to illustrate the 1 node that we said was present with the second MO, these 2 orbitals need to be in opposite phases. So the top can be shaded in, and this one would not be, and the bottom would be shaded in. For this example, let's consider the shaded in one as positive and the non-shaded one as negative. So since the positive and negative are facing each other, there will be deconstructive interaction between the two. Whereas with the bottom one, we had 2 positive faces, and this leads to constructive interference of the p orbitals. So our answer for 4a is this illustration right here. 4b asks us to draw the isomer of C5H8 with conjugated pi systems. So first, let's just identify what a conjugated pi system is. So a conjugated pi system, for example, would be something like this. So you have 2 pi orbitals that are free to communicate with one another, and there's no interruption between the communication by an sp3 atom. So we need 5 carbon atoms. So 1, 2, 3, 4, 5. And since the number of hydrogens is pretty small, this indicates that there are going to have to be double bonds. So we can place a double bond here and another one here. And these 2 are in conjugation with one another. There's no sp3 atom interrupting the communication. Now let's count the hydrogens just to make sure we have 8. 1, 2, 3, 4, 5, 6, 7, 8. Therefore, this is the structure for part B. 4c asks us to draw the isomer of C5H8 with cumulated pi systems. So what is a cumulated pi system to begin with? So accumulated pi system looks like this. You have your double bond, and right in between you have an sp carbon wedged right in between two double bonds. For this problem, I just wanted to start with the accumulated pi system. So let's draw this out. So we have the double bond. So let's just count the carbons just to ensure we got this right. 1, 2, 3, 4, 5. So we have 5, so that checks out. Now let's check out the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 hydrogens, meaning that this in fact is the structure for 4C. 4D wants us to draw the resonance hybrid of the following molecule. So first we can just copy the molecule without doing anything. Next, we are going to move around the pi bonds while maintaining the resonance rules. Please note that the structure is neutral, meaning it has no charge. As we are making our resonance structures, if charge accumulates, we have to make sure that the total charge is 0. We can move this pi bond over onto the oxygen for it to turn into a lone pair. Let's see what the result is. The result is a negative charge on the oxygen and a positive charge on the carbon right here. So why does this happen? Well, we just added an extra lone pair onto this oxygen, and if we just quickly calculate the formal charge, so oxygen has 6 valence electrons and 6 lone pairs and 1 sigma bond, resulting in a -1 charge. So the formal charge on this carbon, well, the valence electrons for a carbon is 4 minus no lone pairs minus 3 sigma bonds. Resulting in a +1 charge. This checks out because we have 1 negative charge plus 1 positive charge, which equals a 0. So the molecule is still neutral, which is okay, and we can proceed further. To change the charge separation, and charge separation simply refers to how close the charges are, so the negative and positive charges are to each other. We're just going to explore the different charge separations by moving this pi bond over here. Now the positive charge has moved on to this carbon. And why is that the case? Well, when we move pi bonds, the charge often moves in the counter direction. So if you're moving this pi bond here, your charge will go in the opposite direction. We can still move the positive charge around. The resulting resonance form looks like this. And similarly, the pi bond moves into this direction and the charge goes into the counter direction, which is why it is located on this carbon here. We can still move this positive charge around by moving this pi bond here. And similarly, we moved this bond here, which caused the charge to move in the opposite direction. So this is our final resonance form. And how do we know this? Well, if we were to move this pi bond here and then put this back, we would just get what we started with. When starting to draw the resonance hybrid, just draw out all the sigma bonds and ignore the double bonds for now. Let's identify all of the locations of our charges. So the only place that we had a negative charge was on the oxygen for all of the resonance forms. Therefore, we can say that the oxygen has a partial negative charge. Now let's take a look at the positive charges. So in this resonance form, there was a positive charge on the carbon, also here, here, and here. Therefore, let's draw the corresponding partial positive charges. So we can identify a partial positive charge here, and here, here, and here. Lastly, we need to identify where the pi orbitals are actually moving around and communicating. So they are communicating around the aromatic ring. So we can draw a dotted representation. Also, the pi orbitals are able to communicate between the carbon here, and all the way up to the oxygen. Therefore, this is our resonance hybrid for part D of problem 4. And that completes problem 4.